Ice, in its varied forms, covers as much as 16% of Earth's surface, including 33% of land areas at the height of the northern winter. Glaciers, sea ice, permafrost, ice sheets, and snow play an important role in Earth's climate. They reflect energy back to space, shape ocean currents, and spawn weather patterns. But there are signs that Earth's great stores of ice are beginning to disappear. To find out where Earth might be headed, scientists are drilling down into the ice and scouring ancient seabeds for evidence of past climate change. What are they learning about the fate of our planet 1,000 years into the future and beyond? About 30,000 years ago, Earth began a relentless descent into winter. Glaciers pushed into what had been temperate zones. Ice spread beyond polar seas. New layers accumulated on the vast frozen plateau of Greenland and across the continent of Antarctica. These ice sheets are monumental formations built over successive ice ages and millions of years. And yet today, scientists have begun to wonder how resilient they really are. Average global temperatures have risen by at least 1 degree Celsius since the Industrial Revolution. They could rise an additional 1 to 3 degrees by the end of this century. Along with rising temperatures come higher rates of melting and rising sea levels. West Antarctica, an area larger than Mexico, is thought to be especially vulnerable. Should it break up, it holds enough ice to raise sea levels by 4 meters or more. Greenland is also showing signs of melting, especially where glaciers, fed by the thick inland ice sheet, meet the ocean. It contains enough ice by itself to add 7 meters to global sea levels. In the coming decades and centuries, rising sea levels could threaten the homes and livelihoods of up to 1/4 of the world's population. With so much at stake, scientists are intensively monitoring Earth's frozen zones with satellites, radar flights, and expeditions to drill deep into ice sheets. And they are reconstructing past climates, looking for clues to where Earth might now be headed. Periods of melting and freezing, it turns out, are central events in our planet's history. Going back over 2 billion years, Earth has experienced at least 5 major glacial or ice ages. These cold periods, and the warm ones that followed, have been spurred by interlocking factors. Volcanic events, the evolution of plants and animals, patterns of ocean circulation, the movement of continents. The world as we know it began to take shape in the period from 90 to 50 million years ago. The continents at the time were moving toward their present positions. The Americas had separated from Europe and Africa. India was headed toward a merger with Asia. The world was getting warmer. Temperatures spiked roughly 55 million years ago, going up about 5 degrees Celsius in just a few thousand years. CO2 levels rose to about 1,000 parts per million, compared to 280 a century and a half ago, and 400 today. But the stage was set for a major cool down. The movement of land masses cut the Arctic off from the wider oceans. That allowed a layer of fresh water to settle over it, and a sea plant called azolla to spread widely. In a year, it can soak up as much as 15 tons of CO2 per hectare. Meanwhile, the Indian subcontinent plowed into Asia, causing the mighty Himalayan mountains to rise up. In a process called weathering, rainfall interacting with exposed rock began to draw more CO2 from the atmosphere, washing it into the sea. With CO2 levels steadily falling, temperatures followed. In the record of more recent times, scientists have been able to track a more subtle climate driver. It was first described by the 19th century Serbian scientist Milutin Milankovic. He saw that periodic variations in Earth's rotational motion altered the amount of solar radiation striking the poles. In combination, every 100,000 years or so, these variations have sent Earth into a period of cool temperatures and spreading ice. Each glacial period was followed by an interglacial period in which temperatures rose and the ice retreated. These Milankovic cycles are not strong enough by themselves to cause the shift. What they do is get the ball rolling. A decrease in solar energy hitting the Arctic allows sea ice to form in winter and remain over summer. Then to expand its reach the following year. The ice reflects more solar energy back to space. A colder ocean stores more CO2, which further dampens the greenhouse effect. Conversely, when ocean temperatures rise, more CO2 escapes into the atmosphere, where it traps more solar energy. Scientists are studying these past climate swings for clues to what could happen in this period of rising temperatures. Greenland today is a laboratory for studying the history of our planet. Its landscapes and fjords tell the story of mountain building, volcanism, ice ages, and the rise of living organisms. From its beginnings in the southern hemisphere, Greenland gradually migrated north as part of what became North America and Northern Europe. The parallel mountain ranges that line its eastern and western coastlines go back 300 to 400 million years. In recent times, the great inland ice sheet that sits between these mountains has ebbed and flowed, with glaciers repeatedly scouring and carving the land. To find out just how dynamic this ice sheet is, scientists have been using airplanes and satellites to look for large-scale changes. Using the GRACE satellite, scientists have been tracking the overall rate of ice loss. The pink shading indicates areas of greatest loss. From 2003 to 2009, the island lost about 1 trillion tons of ice, mostly along its coastlines. They are focusing especially on a series of large coastal glaciers. Before these glaciers reach the sea, the ice flows into a series of narrow channels. They act as dams holding the ice sheet behind them in place. As air and ocean temperatures rise, these ice dams can become unstable and break off into icebergs. This process is called calving. The Jakobshavn Glacier drains into the western coast, producing some 35 billion tons of icebergs each year. The fastest moving glacier of all, Jakobshavn is now surging into the sea at a rate of 17 kilometers per year, 3 times faster than it moved in the mid-1990s. Then there's the giant Zachariah ice stream in the northeast. Once considered Greenland's last remaining stable glacier, it drains the heart of the inland ice along the northeast coast. From 2003 to 2014, it retreated about 20 kilometers and lost 10 billion tons of ice. There are signs that the melting could accelerate. Increasingly in summer, surface meltwaters collect in ponds on the surface of the ice sheet. This is an area just south of the Jakobshavn Glacier, As these ponds deepen, they can begin to drain down through cracks in the ice. That may increase melting by carrying heat down to the base of the ice sheet. When this happens, friction between the rock and the ice above it is reduced, and the flow speeds up. Greenland is losing ice at an accelerating rate. If the entire ice sheet were to melt, much of Greenland would be underwater, dotted with small islands. Over time, with the weight lifted, the land would gradually rise. The sheer mass of the inland ice exerts such a strong gravitational pull on surrounding oceans that it actually raises local sea levels. Ironically, in the event of extreme melting, sea levels would actually drop out to a distance of about 1,000 kilometers. More distant shores would experience an average rise of over 7 meters. How prone is Greenland to melting? Of all the past interglacial periods, perhaps the most is known about the last one, the Eemian, from 130 to 115,000 years ago. At that time, atmospheric CO2 was at pre-industrial levels, and global temperatures were only slightly higher. And yet areas of the far north that are now tundra were found to have been forested. The 19th century Dutch scientist who discovered the period noted the presence of mollusk fossils much farther north than their current range. The thinking today is that higher levels of solar energy struck the northern hemisphere, causing temperatures to rise dramatically in the Arctic. The heat was further absorbed by ice-free seas and by spreading northern forests. The impact was global, with sea levels rising from 4 to 8 meters above present-day levels. To find out how much came from the Greenland ice sheet, scientists have mounted one of the most intensive glacial drilling projects to date. The North Greenland Eemian Ice Drilling Project, or NEAM. The ice samples they obtained told a surprising story. If you were a visitor to northern Greenland at the beginning of the Eemian period, you would have experienced temperatures of about 8 degrees Celsius warmer than today. Yet at the thickest point, the ice receded by only about 25%. Thus, Greenland would have contributed 2 meters or less to total sea level rise. An additional meter would have come from the expansion of ocean water due to elevated temperatures. What caused the additional sea level rise? Scientists are looking to Earth's other, much larger ice sheet, on the continent of Antarctica. Antarctica contains 90% of all the ice and 70% of all the fresh water on the Earth. If you could go back to a time 250 million years ago, what's now the frozen continent of Antarctica was a land of forests and flowing water. In a warmer, wetter world, it harbored a wide diversity of plants and animals. In this period, known as the Permian, Antarctica was at the southern end of a vast supercontinent called Pangaea. In those days, Antarctica basked in the tropical sun. When Pangaea began to fragment, Antarctica moved south as part of the great southern continent of Gondwana. At around 130 million years ago, a series of rifts developed in Earth's crust, causing Gondwana to separate from South America and Africa. Australia finally split off about 85 million years ago, leaving Antarctica on its own. Wind the clock forward to 65, then 50 million years ago. All around the world, warm conditions were slowly giving way to cooler, drier times. Around Antarctica, conifers and other cold-tolerant plants took hold. In some areas, landscapes turned to tundra. Ice remained year-round, gradually forming a thick sheet. At the same time, powerful wind currents circling the pole from west to east drove the circumpolar ocean current. Known as the mightiest current in the world, it helped shield the continent from tropical waters to the north. A combination of factors took hold of Earth's climate. Declining CO2, the isolation of Antarctica, and the tendency of permanent ice stores to reflect more solar energy back to space. At around 2.5 million years ago, Earth entered the last great ice age, the one we live in, called the Quaternary. Year after year, as storms rolled off the oceans, they deposited layer upon layer of snow and ice across Antarctica. Today, it is the windiest, driest, and coldest place on Earth. There are no permanent human populations, only a few thousand scientists and support workers living at scattered research stations. At the Russian Vostok station in July 1983, scientists documented the lowest natural temperature on record, -89.2 degrees Celsius. A recent calculation based on satellite data went even lower, to minus 93.2 degrees Celsius. What little snow falls here stays in place, adding to the continent's mass. You can see evidence of this in the snow and ice that piles up at the South Pole Research Station. This geodesic dome was built in the 1970s. By the time it was decommissioned in 2009, the entrance was nearly buried. With the ice beneath this outpost, 4 kilometers deep, don't expect it to melt anytime soon. That's true in part because of the landmass below it, captured in an extraordinary radar image. The eastern part of the continent, the far side of the image, is a stable foundation of continental crust. In contrast, the western side dips as much as 2,500 meters below present-day sea level. Here, on the Amundsen seacoast, the ice is disappearing at an accelerating rate. Consider how much has already been lost. This is a reconstruction of the continent during the last glacial maximum, 20,000 years ago. Compare it to this image of the current period. Along the western coast, inland ice streams are moving toward the ocean at around 100 meters per year. They end up in floating ice shelves that extend out into the ocean. When ice shelves like this grow, they become prone to fracturing. A giant crack, for example, recently appeared in the Pine Island Glacier. Within 2 years, a 720 square kilometer iceberg had broken off. Scientists are increasingly concerned about what's happening beneath these shelves. In recent times, the Southern Ocean that swirls around the continent has been getting warmer at the rate of 0.2 degrees Celsius per decade. This trend has been blamed for one of the more puzzling twists in the story of climate change. In recent summers in the Arctic, the period of sea ice melting has expanded. The minimum extent of sea ice has been steadily shrinking, and what's left is thinner by over a meter per year in some places. In contrast, the coverage and thickness of sea ice has been growing all around Antarctica. One possibility is that ramped-up winds circling the pole are pushing the ice into thicker, more resilient formations. Another theory suggests that meltwaters have spread a layer of cold fresh water over coastal seas, where it readily freezes. Here's a view of recent changes across the continent from the GRACE satellite. Areas that lost ice are shown in pink and red. Blue indicates ice gains. The greatest losses occurred in West Antarctica, especially where a series of fast-flowing glaciers empty into the Amundsen Sea. European scientists documented this trend with radar data from the Cryosat-2 spacecraft. By tracking changes in the elevation of Antarctic ice, they found that the continent lost on average 159 billion tons of ice each year from 2010 to 2013, an increase of 31% per year over the previous 5 years. A small number of scientists were warning about this as far back as the 1960s. One reason, they pointed out, is the intensification of winds that encircle the continent. As the temperature difference with northern regions has increased, these winds have picked up speed. To sailors brave enough to venture into them, the Southern Ocean once offered the quickest route around the world. Nowadays, stronger winds have had the effect of drawing to the surface relatively warm water that occurs naturally in the depths of the Southern Ocean. These warmer waters have begun to undermine the ice shelves that extend out from inland glaciers. Satellite images from over a decade ago show the effect this can have. Out on the West Antarctic Peninsula, the Larsen ice shelf extended out over the ocean. This image from early February of 2002 shows Larsen beginning to splinter. By March 7th of that year, it broke apart. Countless icebergs tumbled into the sea. Without the shelf's buttressing effect, the glaciers behind it picked up speed, dumping an additional 27 cubic kilometers of ice into the ocean each year. That's not the only place where it's happening. One team set up its base on the Pine Island Glacier, where it juts out into the Amundsen Sea. From the surface, they drilled down through 500 meters of ice to track changes in temperature, salinity, currents, and ice volume. They found that warmer waters had been eroding the underside of the ice shelf, with melt rates of about 6 centimeters per day, or about 22 meters per year. Another group has been using satellite and airborne radar to track changes like this on a regional scale. Red shows where the glaciers are traveling at their highest speeds, at the intersection of ice and ocean. Now look at where the glaciers push out into ice shelves, like the one at Pine Island. Down here, the flow speed is steadily increasing. Some of the most dramatic changes have been observed on the Smith Glacier, one of the smallest in this group. Back in 1996, this is where water, ice, and land met beneath Smith. By 2011, that so-called grounding line had moved 35 kilometers further back, a retreat of more than 2 kilometers per year. Now peel off the ice from the continent. The red arrows show the highest flow rates. You can see that these fast-moving glaciers sit within valleys, some of which are below sea level. The more the grounding lines retreat, the more seawater can creep into these subglacial basins. For most of the glaciers, there are no major barriers, such as hills or mountains, that would slow them down once they got going. The more the glaciers speed up, the more likely the ice sheets behind them will collapse. If that happens, it may not be completely due to climate change. Scientists have found that the flow of water beneath some glaciers is too high to come just from seawater. The Transantarctic Mountains, dividing East and West Antarctica, are the product of a rift that is occurring in the underlying crustal plate. Scientists have detected seismic activity they say is consistent with magma moving within the crust over 25 kilometers down. They have now found there is a significant amount of geothermal activity beneath one of the largest glaciers, the Thwaites, to account for the extra melting. To date, most studies of future sea level rise have focused on the ice sheets of Greenland and Western Antarctica. Together, they could account for up to 12 meters of sea level rise. The massive East Antarctic ice sheet has been largely ignored. Because of its sheer size and unwavering cold, it has seemed impervious to warming trends in the north. New research has given scientists reason to wonder how stable it really is. If any part of East Antarctica is vulnerable, it's here, in a region called Wilkes Land. Under the weight of ice today, some parts of the basin are over 2 kilometers below sea level. There is enough ice here to add another 3 to 4 meters of sea level rise. Currently, the Wilkes ice sheet is said to be in balance. This means the amount of ice that melts or falls into the sea is replaced by new ice that forms inland. What would it take to throw Wilkes out of balance? A crucial factor is a zone in which the ice shelf is wedged against a series of ridges on the sea bottom. These ridges act as a stopper, preventing the glacier and the ice sheet behind it from moving forward. If warmer waters were to undermine the ice that rests on these ridges, then the ice sheet could begin to move out to sea. The effect has been described as similar to a bottle of water that's tilted downward. Remove the stopper and gravity empties it out. Once the ice starts flowing, there would be no stopping it. How plausible is this scenario? On the much smaller Pine Island Glacier, scientists have shown that the ice shelf has already broken free of an undersea ridge. The disintegration of coastal Antarctic glaciers is a process that would take centuries to run its course. But once it gets going, it would mean a steady rise of sea levels for the foreseeable future. A recent study sought to extrapolate changes to Antarctica during two interglacial periods, the Pliocene, 3 million years ago, and later on, the Eemian. Factoring in the current rate of ice loss in Antarctica, the study concluded that sea levels could rise a full 2 meters by the end of this century. By the year 2500, the ongoing loss of Antarctic ice could send sea levels up by more than 15 meters. The danger is that even if we bring greenhouse gases under control, the additional warmth being stored in the ocean might soon lock us into centuries of continued melting. How will that affect the way we live over the next 100 or 1,000 years? The changes we experience in our everyday lives are shaped mostly by near-term developments in technology, politics, and culture. Some of the bedrocks of modern life, cities like New York, London, Hong Kong, and seaports around the world have grown and evolved on the scale of centuries. Within the long arc of their histories, rising seas could threaten their existence in a relatively short time frame. Add to that networks of coastal communities and businesses lost, and hundreds of millions of coastal residents forced to move inland. The emerging story of ice sheet melting and sea level rise is often couched in uncertainties. With the drama of what's happening damped down by the rational language of science. Critics focus on margins of error inherent in the scientific process, or downplay the predictive power of computer simulations. Politicians debate. Conspiracy theories abound. With each passing year, our choices narrow. The history of Earth's great ice sheets contains a stark lesson for our times. In periods of rising CO2 and temperatures, the ice draws down and sea levels rise. What's at stake for Earth in the coming centuries and millennia is the world we know, the one that has nurtured and sustained us. The Earth itself will go on, ever-changing on short and long time scales. A dynamic, living planet.